By the end of this video, we will understand how to simulate data from a target distribution using nothing other than its CDF and a random uniform. Let's get started. An actuary is using the inversion method to simulate a random number from a distribution with the following density function. F of x is equal to 5 times x to the power of 4 in between values of 0 and 1. A random draw of 0.6 was chosen from the uniform distribution between 0 and 1. Calculate the simulated random number. For this problem, we need to know two things. So first off is how to convert a PDF to a CDF, and that's by integrating the PDF from the minimum possible value up to the value of interest, assuming it's continuous, and a few other things. But so here in this problem, that's going to correspond to going from 0 to whatever x we care about. So you need to know for this problem how to take the antiderivative of a polynomial function, as well as this property between the PDF and the CDF. The second thing you need to know is what the inversion method is. So just conceptually, why is this kind of important or useful? So when you want to say, go into R and code up a simulation and say randomly simulate a value from the normal distribution or from the gamma distribution or something like that, I would imagine, I don't know this for sure, but I would think they would use the inversion method behind the scenes in that code to do that. So really all you need to have to do is be able to simulate things from a random uniform distribution. And if you can do that, as well as determine the inverse CDF function, you can simulate data from any distribution of interest. So again, the reason this is useful is you have the CDF and you can invert it, then you can simulate data that follows that target distribution, whatever it may be that you've created. So the way that you can go about doing this is, we have this PDF of interest. So here we have some distribution. Values fall in between 0 and 1200, and all I've done with these colors is denote 10% buckets or deciles. So 10% of the time we see the data falls in between 0 and 190, and then 10% of the time the data falls between 190 and 220 in this specific case. So I'm just following along in these colors. They're all corresponding to 10% buckets. Well, what we would then do is, we need the CDF, so we convert things to the CDF. So now we don't care about the area, it's the Y value. So CDF is the probability of being less than or equal to a given value. So here we see 10% of the time you're less than 190, and then 10% of the time 20% of the time you're less than 220. And that corresponds to, well, what's the probability of falling in between 190 and 220? It's going to be 0.2 minus 0.1, or again, just another 10% bucket. So then finally, for the inversion method, we have this function. So the inverse CDF is if you swap the x and y axis, right? And we can just do this visually with these lines I've drawn, where we'll pick a value on the y-axis we care about and then look up the corresponding x value. That's the same as taking the inverse function of the CDF. And all we have is that relationship, as well as the ability to simulate from a random uniform. And so again, with these colors, all I'm showing here is, uniform 10% of the time is going to be less than 10%, 20% of the time is going to be less than 20%. So no surprises there. And if I were to simulate from a random uniform, I could then go to the y-axis of my CDF and look up that corresponding value. So in our specific problem, that value is 0.6. So if we simulated a 0.6, we would then say, okay, well, what x value does that correspond to? Oh, it corresponds to 475. And so what I'm going to do is say that because I randomly drew a sample of 0.6, I'm going to say that I simulated a value of 475 for my target distribution of interest. So then finally, just as a justification or something that hopefully makes this make more intuitive sense, if that wasn't sufficient, in terms of the inverse of the CDF doing what you want it to do, is we know that we're simulating from a random uniform, and 10% of the time it's going to fall in this shape here. And then 10% of the time it's going to fall here, and 10% of the time it's going to fall here, so on and so forth. We also know that 10% of the data, according to our target distribution, is in that area by definition. That's how I drew this out. And if you're not convinced that it will follow this shape, right, you think, well, how do I know it's not 10% equally distributed here? I picked 10 buckets arbitrarily. And so you can take this to the extreme limit, and as these buckets, you have more and more buckets. Let's say there's 100 buckets and there's a 1% chance of it falling within each range. Maybe that hopefully you can conceptually visualize that and see why using the inverse CDF with a random uniform is just going to provide you with the target distribution of interest. So hopefully that wasn't too much rambling. But yeah, that's how, given a uniform, if we can invert our CDF, we're able to simulate any distribution of interest. So now for the specific problem, the first thing we have to do is, again, we care about the inverse CDF. So we need to convert our PDF to a CDF. So we know that our PDF is 5t to the power of 4. I converted it to t, so we can then integrate from 0 to x. So again, the domain possible values are going to be from starting at 0 up to whatever x value of interest with a maximum value of 1. The antiderivative of 5t to the power of 4 is just t to the power of 5, because you can see if you take the derivative of this, 5 comes down, and then 5 in the exponent becomes 5 minus 1, which is 4. So this is the antiderivative. And then finally, when we plug and chug, what is x to the 5th minus 0 to the 5th? It is just x to the 5th. Also, conceptually, we can confirm that this is a CDF just because when we plug in 1, the maximum value, 1 to the power of 5 is 1. So the CDF does eventually reach 100%. So we have our CDF, and now we could calculate or derive the inverse CDF, but since we're only simulating for one specific value, we can actually just plug and chug for that specific case. So we know that the CDF, we want the x value that corresponds to a CDF value resulting in 0.6. So we do 0.6 to the power of 1/5, and we just get our answer of 90.29%. Or, excuse me, these aren't percentages. I should have just said 0.9029. So scrolling back up, we see that falls in the range of E, so E is our final answer. If you find these videos helpful, please consider subscribing, commenting below, letting me know if there's any other content you'd like me to cover other than just specific past exam questions. As always, I really appreciate you taking the time to watch